All right, welcome to magnetism. At this point, you need to have printed up the files that I've posted on Facebook, or eventually I'll probably have them on my web page. And you're going to need these pages in order to follow along. Well, let's talk about magnetism. Let's start out with the simple things. First of all, magnets have a north and south pole. You cannot have a monopole magnet. Sorry about the writing, that's a monopole magnet. In other words, a single north or a single south cannot exist by itself. Also, be aware, you should not confuse magnetism with static electricity. On static electricity, you get positive and negative charges, and they can exist in isolation. You can have a single positive and negative by itself. You cannot have a north or a south pole by itself. A couple other things to remember. First of all magnetic fields are caused by moving charges. We'll be going into that a lot in a lot more detail. In a wire, magnetic fields are caused. Current causes those magnetic fields. In a permanent magnet, it's the electrons moving around the nucleus that are going to cause the magnetic fields. Now, to determine the direction of a magnetic field, we use a very simple device. We use a compass. A compass is simply a north-south bar magnet mounted on a small needle bearing that allows it to move around. Now, I drew it like this, but most of the time you're going to see me just draw an arrow. The arrowhead is going to be pointing in the north direction. And the definition for the direction of a magnetic field is the direction the north pointer will aim in that magnetic field. Now, before we go into that, let's add one other quick thing. Right on the side here, please remember that like poles are going to repel. Whoops, south-north. These guys are going to repel. And the opposites, north-south, south-north. Whoops, sorry. Goofed that one up. Let's clean that up. North-south, north-south. And those guys are going to attract each other. They're both going to pull in. These guys are going to repel each other, which means the north pointer of the compass is always going to be attracted to a south pole and repelled from a north pole. So if I was to, as you can see, I've drawn in the directions that the north point of the compass is going to aim when it's near this bar magnet over here. Notice it's getting the north side, which would be right here. South would be there. It's getting pushed away from the north side, and the south being attracted to it. So it's going to point like that, and this is going to give you the general direction of the magnetic field going around the bar magnet. I included some field lines on the top here to kind of fill in that field, and I can put another one down here. Kind of out, around, but it doesn't stop right there. The magnetic field continues right through the bar magnet. This leads to 4 rules for magnetic fields. The first one is outside or external of the bar magnet, the fields go from north to south. Internal of the bar magnet, they're going to go from south to north. They never cross, and they always form closed loops. Okay, now even if you've got a field that comes off the end here, goes out into space, comes back in on the other side, it's still going to just form a closed loop. Now, if I take a look at a horseshoe magnet down below, all that horseshoe magnet is a bent bar magnet. So you're going to get a field line coming out from the north, going into the south, out from the north, going into the south, out from the north, going into the south, just like this. And they're going to continue right through the interior of that magnet, just like this, following the same rules. Other things that you should keep in mind, as in any field, close field lines mean you've got a strong field. Far apart it's going to be a weak field. So far, now just to give you an idea, we've got multiple bar magnets. Well, north-south and north-south, you're going to have the field lines going from the north to the south. And they do continue through. I'm not going to bother drawing them, but they do continue through. And then they loop around over to the other end of the south. Yeah, there will be some field lines going across here, and those are the obvious ones when you map it, but this is what we're looking for. This is what happens when you take a single bar magnet and break it into two. You wind up with two brand new bar magnets, continuing right through. If I've got like poles near each other, well, the field between the two magnets kind of gets squished, and the other end gets bowed out. So you wind up with something that goes like this, out, but then it gets kind of compressed in on this side, out, around, a little compressed in on that side, and you get the same thing here, out and around, but a little squeezed in on this side, out and around, and I don't want to go through those, don't want to cross the field lines, like that. And that's pretty much it. Yes, someplace in there, there will be no field.